All right, so now we're going to bring calculations into it. Like I said in the last video, we're going to bring a decimal place into what we've been talking about. We're going to bring some numbers into play. So when we have a system that starts out not at equilibrium, maybe we create a solution and it's got to equilibrate. We dissolve some stuff and then it's going to react with the water or something else that's in the solution, and it takes time. So we know our initial conditions, but we don't know where we're going to end up, but we do know the equilibrium constant, so we can calculate it. And that's what we're going to work on here. So we're going to use KEQ to find equilibrium conditions if we don't start at them. So we know what we started with, we know what KEQ is, we can figure out where we end. We can figure out what equilibrium is going to look like. That's where we are now. And to do this, it's only done in 5 simple steps, okay? So first we got to ID our products and reactants. So along with that, so you got to know K. Maybe you have to look it up in the back of the book. I think it's, well, I got on my notes here. Appendix 23 in the back of your book if you ever need one of those values. So you need your reaction, you need the K that goes with it, okay? Then you got to determine initial concentration. So oftentimes these will be teased out to you in the question, if not outright given you. And then we're going to set up a Rice table. We're going to talk about what that is. Incredibly important, by the way, for the end of this chapter and all of the next 2. So you're going to want to make sure you're comfortable with these. And then we're going to solve for our change in X. Again, we're going to explain this. And then we're going to find out what our equilibrium concentration values are. So that's what we're going to do. This is sort of the blueprint. This is the process. We're going to put it into action, all right? So let's see here. We have some acetic acid. We dissolve 1 mole of it in 1 liter of water at 25 degrees Celsius. And we know what KEQ is at 25 degrees Celsius because I looked it up in the back of the book, all right? Now, why am I putting the temperature here? Well, equilibrium can shift with temperature. And how do we account for that? Well, we actually account for it by having different equilibrium constants at different temperatures, just like we did with reaction rate constants. So if you don't see a temperature pairing up, assume they go together. But I just wanted to be very specific here because I didn't talk about it in that video. And so this is mathematically how we address, shifts to temperature. Okay, so our Rice table has 4 parts. It's an acronym, turns out, surprise. So sometimes it's also called an ICE table in other books. Your book calls it a Rice table, so I'm calling it a Rice table. But you got your reaction, which I've already written out. So I've got my acetic acid, CH3COOH. I got my acetate as a product, CH3COO-. So acetic acid will react with the water. It dumps off an H+ on the water, makes H3O+, and the acetate anion is left behind. So that's our reaction, and it is reversible. So this is what we call an acid-base reaction. Whole chapter on that. We'll talk more about it in a little bit just to prime you for it. So that is our reaction. So I is initial concentration. Well, this is some hard math I set up here. If I've got 1 mole dissolved in 1 liter, I got 1 mole per liter. This is 1.000 molar, okay? This isn't gonna matter. What's the concentration of water? I don't know. Skip. It's a pure phase. It doesn't show up in our equilibrium constant. We don't have to worry about it. All right, because it's not going to show up in our equilibrium expression, so we're good. This guy, well, initially, I didn't add any. It's at 0. I didn't add any H3O+ either. That's at 0. Okay. So this is just our initial setup. All of this should come out of the question. Okay. Now change, this is where it gets tricky. I'll actually be a little bit more specific here. We'll say Na. I'll use dashes after that because I'm lazy, but I don't want anyone thinking that's like something minus something like Na. Does not apply. Not applicable. All right, so change in concentration. Well, this is where our friend X here shows up. So this thing is not at equilibrium, right? Equilibrium, we have a K value that's, it's not 0. So it's going to form some product here. So the change is going to be a shift to the right. So that means I'm going to lose some amount of CH3COOH. So I'm going to say minus X. I'm going to say minus 1X here because I only use one of these. So for every one of these I lose, again, this guy doesn't matter. And for every one CH3OOH that I react, I get one acetate, so I'm going to say plus X. And for this guy, I get one as well, for the hydronium ion here, H3O plus. So that's plus X. All right, so for every acetate, or I'm sorry, every acetic acid that I react, I generate an acetate and a hydronium ion. Okay. I don't know how many I'm going to lose, so I'm just going to call it X. That's our variable. All right, and so our equilibrium concentration, well, I'm going to have this plus whatever the change is. So it ends up being 1.000 minus X. I'll lose some amount X, whatever's left over. I have at equilibrium. This guy doesn't matter. Over here, I'll have 0 plus X, so I'm just going to write X. This is 0 plus X, so I have X. So my equilibrium concentration of acetic acid is 1 minus X, with some zeros for accounting. And then for acetate, it's X, and hydronium, it's X. Well, if I write my expression for KEQ, what am I going to have? Well, I'm going to have products over reactants, so I'll have this guy, concentration to the power of 1. So I'll have my acetate, CH3COO minus, times my concentration of H3O plus, only one of those, so it's just to the power of 1. All right. And I'm going to divide by acetic acid's concentration, stoichiometric coefficient of 1, so again, just to the power of 1. So CH3COOH. And these are all the concentrations at equilibrium. Gets me KEQ, right? Well, these are my concentrations at equilibrium, so I'm going to substitute those in. So I don't have the numbers yet, but I've got something that represents the numbers, and so I'm going to use that. And so what's the concentration of this guy? Well, at equilibrium, it is X. Concentration of this guy, it is X. All right. Concentration of this guy right here, 1.00 minus X. All right. Or I can say that this is X squared over 1.000 minus X. So that's the first part of the setup. So so we're all the way to step 4 right now. Step 4 is a doozy, by the way. Not bad, not bad, not too bad. This gets a little tricky till you get the hang of it. And then this is where we really start grinding against that calculator. Wear out those button pushing fingers. So KEQ equals this, but it also equals this number right here. So all of this is going to end up equaling 1.76 times 10 to the minus 5. All right, and this end over here, this is where all of our focus shifts. Everything we did before was to just get that set up. We've got some conglomeration of x's equals the number from the table, okay? So being able to go from here to here, very important. Being able to go from here to here, very important. And then we get into the math, all right? And so I'm going to rewrite it down here. I've got x squared over 1.000 minus x equals 1.76 times 10 to the minus 5. All right. Well, I can do a little math here. I'm going to go to the right, not down, because I don't have much boardroom left. And I'm going to multiply both sides by the denominator. So I get x squared equals 1.76, as you can clearly see, times 10 to the minus 5 times 1.000 minus x. Okay. And then I'm going to just multiply all this through, so I get 1.76 times 10 to the minus 5 minus 1.76 times 10 to the minus 5x. All right. So I just multiplied this number times 1 and times negative x. And so what I'm setting up for, if you haven't noticed, is I'm setting up for a quadratic equation. So I'm setting up for a quadratic formula. So I'm going to want 0 on one side, and then something times x squared plus something times x times some other number. I'm sorry, not times, plus some other number. Keep in mind any of those numbers could be negative, so it might be a subtraction. All right, so I am going to take my x squared, and I'm going to subtract all of this from both sides. So what I get is I get x squared. I'm going to write in a very specific format here, plus 1.76 times 10 to the minus 5x minus 1.76 times 10 to the minus 5 equals 0. All right, so this is a quadratic equation. I'll write this a little smaller here, so I got some room underneath it. So we have ax squared plus bx plus c equals 0. Okay? So let's have some fun with this. Let's use multiple colors here. So we'll go bx in green and c in red here. And so this is c. This is b, and then there's a 1 here that we're not writing because we're normally not going to do that. But all right. And 1. So a equals 1, b equals 1.76 times 10 to the minus 5. And you're going to think, how can I solve this with so little room left? Well, I'm going to leverage technology. And you can too. So your new best friend, and I'll try to remember to post a link or two on the Moodle page to some reliable versions, but your new best friend is going to be a quadratic formula calculator, quadratic equation calculator, quadratic equation solver. However you want to Google it, you will get results and you will like them. And it's just going to ask you what's A, what's B, what's C. And I just go A is 1, B is 1.76 times 10 to the negative 5, C is 1.76 times 10 to the negative 5. And it's going to spit out answers for x. And it's going to go, so I'm just going to say solve. Whew, magic. All right. And I go, okay, I plug it into my quadratic formula calculator, and I get x equals 0.00419 molar. Now you're going to get 2 answers for x. That's the one you keep. You can't keep the other one because if you have a negative value for x, because that's what we get a positive and negative value here. Well, if I subtract a negative number, I end up with more acetic acid than I started with, and that is not physically possible. So there are 2 mathematical solutions, and then there's only one that works in reality, and it's this one, okay? So, what is the answer to the question? Because it's not just find x, it's use x to find the solution. Now it turns out that in this case, my acetate equilibrium concentration actually is x. So that is my final answer. That is my concentration of acetate. Man, I filled this board up. By the way, I had to write this thing like 3 to 4, maybe even 5 times to just get that up there as much as possible because I knew I was going to need as much board space. I wanted to leave this over here so we can refer back to it in a minute. So I was like really fighting for space. You guys have no idea how hard I worked for this one. No respect, I tell you. All right. So we just solve for our change in x, and then to solve for equilibrium concentration values, I got to go back up here, and it just turns out it's x. Now, if I need to know my equilibrium concentration of acetic acid, then I would have to go 1 minus x, which should get me like 0.996, something like that. So I'd have to do another step there. I'd do a little bit of math instead of just being like, oh, x is the answer. It's not always. It wouldn't be the answer here because it's not x. The other thing is, if you ever have any products or reactants, it's going to be x times their stoichiometric coefficient. You know, if this broke up and made 2 of these, for every x of these I lost, I would gain 2x, and so you got to keep that in mind as well. So maybe you have to multiply by 2 or something. Not the case here, just a heads up. So, you got to go through. So, ID reactants and products, right there. Now I had to kind of conserve space a little bit. So I kind of worked that into the Rice table. Which, by the way, it's our reaction, our initial concentration, whatever change there is to reach equilibrium, and then what do we get at equilibrium? What is the concentration? So that's Rice. It's more fun when the book says an ice table, because then I can start being like dun 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 ch, dun dun dun, you know, ice ice baby. It's a little weird to be singing Rice Rice Baby, so I don't tend to do that. All right, so we determined our initial concentrations. That's got to be given to you in the question. All right, set up our Rice table. Okay. Fill it in. What are our initial? We know our reaction, we know our initial. What's the change going to be? And by the way, I could have put plus or minus x here. It wouldn't have actually mattered. But it's generally good to think which way is it shifting and do that. So generally you want to do minus x here because we are going to shift towards our products if we only have reactants. So I did that. But if you'd put plus x here, then we would have a minus x, and then you would have just had an x that was negative down here, and then you would have flipped the sign to get your acetate concentration. So it'll still work. It's not like you can poison the well all the way up here. It just makes it a little more intuitive if you take a second and think about, is it going to go this way or is it going to go this way? Did we only start with products? And is it going to shift towards reactants? You know, you want to think about that. All right, and then we just add these terms together to get this one. Didn't matter. 0 plus x gets us x. 0 plus x gets us x. All right. And then we write our expression for KEQ. We plug in our equilibrium values to it with our variables. And then we rearrange into a quadratic formula. Then which we have here. Then we plug these numbers into a quadratic formula calculator. It's going to save you a lot of time. And you are going to get x. All right. And then you'll get 2. Quadratic formula always have 2 solutions, so you got to choose carefully. Make sure you pick the right one. You can't have more of something than you started with, especially if you're still going to have, and you can't have negative concentrations either, by the way. Like, how would I have a negative concentration of acetate? So you can't keep the negative number, we got to keep the positive number. So 2 mathematical solutions, only 1 real solution. So you have to think carefully there. And then sometimes you have to perform a little math with x to get your answer. And that's all there is to it. So I'm going to make one more video for this class. We are so close to the end, so close. One more video. I'm going to show you some other math tricks. You should always have a quadratic formula calculator at your disposal in this class. But you might not in the next one. So I'll show you some tricks to get around. You know, you could go, you know, what is it? It's negative b plus or minus, is it square root of a squared minus 4 minus, no, oh, it's all gone. Oh boy, over 2a, blah, 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 blah. Quadratic formula, calculated by hand. Clearly I have it totally memorized. Minus square root of b squared minus 4ac all over 2a. Okay, that's it. All right. Whew. I'm sure if I cut that up right, I'll have said the right thing. The power of editing. All right, so one more video. I'll show some math tricks for when you don't have a quadratic calculator in hand. And they will prove to be very helpful in 223 as well. So I'm going to do that. And this system right here would have qualified for it. So if you're feeling kind of mad at the end of the next video that I didn't just do that on this one, cool, you get the math trick. Congratulations. If not, you can always quadratic calculator your way through it for this course, which is nice. I wish I could give people a quadratic calculator in class. I really do. because this is a chemistry class, not a math class. I'm aware of that. Unfortunately, we have to do some math that touches right at like the highest level of stuff they talk about in the prerequisite course of Math 95 to be able to talk about this and actually solve it. But ultimately, I don't want to make you just grind out the quadratic formula by hand when there's electronic systems that can do it automatically. So please take advantage of that. Out of all this, that is one nice thing, that I actually have a class that can do that. All right, so one more, and then that's a quarter.